let's do a related problem. I'll write it as a separate problem, and the problem number would be 5. So problem 5 is, for the same G as GLNR and S as Rn as in problem 4. Okay, show that if A satisfies if A is a matrix, invertible n by n matrix, such that A dot V is V for all V in Rn, then A is the identity matrix, identity n by n matrix. Why is this? Okay, so any matrix which fixes every vector, so in other words, it's in the stabilizer of all vectors or all elements of the set S, then it must be the identity element. Why is this? So we already saw that A E1 equals E1 implies the first column right, this we have already seen in the previous problem, and AE1 is equal to E1 because AV is equal to V for all V. So now AE2 is also equal to E2, right? E2 is the second elementary vector. So 0, second entry is 1, then followed by zeros. This implies, so A is already, we know this, but second column can be anything at this point. So it's A12, A22, A2n, A1n, A2n, ANN multiplied by 0, 1, 0, 0, 0 must be 0, 1, 0, 0. And exactly the same calculation as before shows that this implies, what is this product? This picks out the second column of the matrix. Because when you multiply it out, the second column is picked out. This is 0, 1, 0, 0, 0. That means if E2 is E2, the second column of A is E2, right? We already know the first column of A1, A is E1. Now we know AEI is equal to EI. So the ith column of A is EI. So now this is true for all numbers from 1 to n. So the first column of A is E1, second column is E2, third column is E3, fourth column is E4, nth column is En. But this means A is identity. Right? So if A fixes, in fact, the problem asks you to show that if AV is equal to V for all V in Rn, then A is identity matrix. It suffices to show actually assume that AE1 equals E1, AE2 equals E2, AEN equals AN. But of course, if you think about it a little bit, if AEI is equal to EI for all I, AV will be equal to V for all V. This is because the vectors E1, E2, En span the vector space Rn. That is, if you know this, but it's not important for this problem. So this action has the property that if a vector, if a group element is in the stabilizer of all vectors, then it is the identity element. So this action is an example of faithful action. Okay, so I will define this now, which I have not defined earlier. So definition: let a group G act on a set S, we say that the action of G on S is faithful. We also say sometimes, or G acts faithfully on S. So action of G on S is faithful, or G acts faithfully on S if G is an element such that GS equal to S for all S in capital S. This implies that G is identity, right? So if G is an element of the group that fixes all elements in the set, then G is identity element. Okay, so this is an important class of actions. So G acts faithfully on S. So other examples include action of G on itself by left multiplication is faithful, and this is exactly what we used in the proof of Cayley's theorem. On the other hand, action of G on itself by conjugation is not faithful in general. So for example, if G is abelian, then orbit of GS is G. That's what we stabilizer is G for all, as we saw earlier. The orbit is G, right? This is one of the problems that we did earlier. So certainly the intersection of orbits, intersection of stabilizers is all of G. On the other hand, this is a problem that I'll leave for you as an exercise. I won't do, but it is the immediate consequence of the problem on the relevant problem here. So problem 6, show that, so maybe I'll write it in the new slide. Problem 6, show that the action of G on itself by conjugation is faithful if and only if the center is trivial. Okay, the center I have defined also in the previous problems. See, if G is abelian, it is very far from being faithful. It is in fact the diametrically opposite to being faithful, because faithful means intersection of orbits is trivial. Sorry, intersection of stabilizers. I keep confusing between orbits and stabilizers, but faithful means intersection of stabilizers is trivial. But if it's abelian, all stabilizers are the group G. So certainly it's not faithful. So faithful and abelian are at the opposite ends of the spectrum as far as conjugation action of G on itself is concerned. So faithful and opposite spectrum of abelian is the center being trivial. Center being the whole thing is abelian, center being trivial is the opposite thing. So if the center is trivial, the action of G on itself by conjugation is faithful. Let's finally do one more example. This is computational to compute equivalence classes and orbits. So consider, let G be S3, compute the orbits for the action of S3 on itself by conjugation. Remember, action of S3 by itself by left multiplication, orbits are only one. There is only one orbit. So that's not interesting. And stabilizers are all trivial. Okay, so operation or action of S3 on itself by conjugation is more important, more interesting. So let me use this representation of S3 cycle notation. So 1 2 1 3 2 3 1 2 3 1 3 2. Okay, let's use the a quick piece of definition. Orbits for the action of G on itself by conjugation are called conjugacy classes. Okay, so this is an important notion. So this is exactly as orbits, it is just a new word. Conjugacy classes is the word in the specific example of the action of a group on itself by conjugation. Okay, so this is useful to, because the action of a group on itself by conjugation is an extremely important example of group action, and this is very important in proving various important theorems. So the orbits are given a special name in this case, they are called conjugacy classes. So the problem 7 is simply asking you to find conjugacy classes of S3. That is just a shortened version of saying find the orbits for the action of S3 on itself by conjugation. In other words, find conjugacy classes of S3. Okay, so what is the orbit of E? It is simply, remember, orbit of E for the conjugation action is just E, because we have to do GE, G inverse, as G is in G, but this is just E, right? The action is by conjugation, so you vary small g and take GE, G inverse, so this is okay. Now find the orbit of, let's say, 1 2. So we want to do G 1 2 G inverse as G in varies in S3. Okay, so this is a quick calculation, so let's do one by one. So E 1 2 E is 1 2, that's always there, so 1 2 is always in the orbit. What about 1 2 1 3 1 2 1 2? What is the inverse of 1 2? So this is 1 2 1 2 inverse is again 1 2, this is 1 2, right? 1 2 1 2 is identity, then 1 2, so that's not surprising. So the new thing will be if you take 1 3, so let's do 1 3 1 2 1 3 inverse. What is 1 3 inverse? It is again 1 3, so I have to vary G and compute G 1 2 G inverse. And what is 1 3 1 2 1 3? If you do the calculation quickly, 1 3 1 goes to 3, 3 goes to 1, so 1 goes to 1, 2 goes to 1 and 1 goes to 3, and 3 goes to 1, 1 goes to 2, so 3 goes to 2. Similarly 2 3 1 2 2 3, because the inverse of 2 3 is again 2 3, will be I will let you calculate this quickly. It is 1 3, because 1 goes to 2, 2 goes to 3, 3 goes to 2, 2 goes to 1, so 3 goes to 1, 2 goes to 3, 3 goes to 2. Okay, so now let's do 1 2 3 1 2. Inverse of 1 2 3 is 1 2 3 1 2. Inverse of 1 2 3 is 1 2 3 1 3 2, if you think about it for a minute. So this would be 1 goes to 3, 3 goes to 1, so that's 1. 2 goes to 1, 1 goes to 2, 2 goes to 3. 3 goes to 2, 2 goes to 1, 1 goes to 2, so this is 2 3. And finally 1 3 2 1 2, and 1 3 2 inverse is 1 2 3, and this will be 1 goes to 2, 2 goes to 1, 1 goes to 3. 3 goes to 1, 1 goes to 2, 2 goes to 1. 2 goes to 3, 3 goes to 2, so this is 1 3. So what is the conjugacy class? Of 1 2, or the orbit of 1 2, this is equal to 1 2 certainly will be there, 2 3 is there, and 1 3 is there. So in fact we get all 2 cycles or all transpositions, right? This is, so now recall the splitting of S as a union of disjoint orbits. So S3, remember, must be a disjoint union of conjugacy classes. Disjoint union of orbits, in this example we are calling them conjugacy classes. And so far we have found two of them. So far we have found E, that's one conjugacy class, and all two cycles form another conjugacy class. So this is one conjugacy class, this is the second conjugacy class. So far we have managed to account for 4 elements of the symmetric group on 3 letters. The remaining 2 elements must be also part of some conjugacy classes. So find the orbit of 1, 2, 3, let's say. So in order to find orbit of 1, 2, 3, let's find the conjugate of 1, 2, 3 by 1, 2. 1, 2 inverse as before is 1, 2. So 1, 2, 3, 1, 1, 2, 1, 2, 3, 1, 2. Let's compute this. 1 goes to 2, 2 goes to 3. So 1 goes to 3, 3 goes to 1 and 1 goes to 2. So 1, 3, 2. 2 goes to 1, 1 goes to 2, 2 goes to 1. So 1, 3, 2. So this means 1, 2, 3 is related to 1, 3, 2. And now you are able to conclude that. So we can conclude that 1, 2, 3 and 1, 3, 2 is a conjugacy class, right? Because, so remember we have to find one more. This must be the conjugacy class. Why is that? These are already part of a conjugacy class. 1, 2, 3 and 1, 3, 2 are related, so they are part of a conjugacy class. But can there be anything else in this conjugacy class? No, because S3 has only 6 elements and the remaining 4 elements are already accounted for. If any of them is in this conjugacy class will have a non-empty intersection with them. But conjugacy classes need to be disjoint. So this is the conjugacy class. And you can also check direct by calculation that all other conjugates will be equal to one of these. But we don't need to do that. So the conjugacy class decomposition of S3 would be E disjoint union with 1, 2, 2, 3 and 1, 3, disjoint union with 1, 2, 3, 1, 3, 2. Now let's observe one thing. When I talked about counting formulas, I noted that the cardinality of the set of the group of the set, which in this case is again the group, is the sum of cardinalities of orbits, right? And I also noted at that time that cardinalities of orbits divides the order of the group. So in this case, what is that formula? This is called the class equation. Okay, so in the case of a group, a finite group, I will define this more formally later when I come to this later in a video. In the case of a finite group acting on itself by conjugation, this statement that the cardinality of S or the cardinality of the group, which is also the set in this example, equal to order of one element, orbit of, it's equal to the sum of sizes of orbits, is called the class equation. So of a finite group G acting on itself by conjugation, it's called the class equation of G. This is a very, very important piece of data attached to a group. Okay, so as I said, the action of G by itself on itself by conjugation is a very, very important group action, and the usual things that we have in all group actions are given special names in this case because of the importance of this example. So orbits are called conjugacy classes, and this formula here is called the class equation. So the class equation of S3 is, so you have 6 is the cardinality order of S3, one orbit is just containing identity, that's 1, the other orbit contains all 3 cycles, there are 3 of them, and the final orbit contains 2 cycles. So this is 1 element, this is 3 elements, 1 element, 3 elements, 2 elements. So the class equation is 6 equals 1 plus 3 plus 2. And remember this another point that we made earlier checks out. Each numbers that appear in the class equation must divide the order of the group, which is 6 in this case. 1 divides 6, 3 divides 6, 2 divides 6. Because these are orbits and the counting formula says that orbit size divides the orbit of the group. Now using this you can also compute the stabilizers of these elements. Because remember orbit of 1 2 is 1 2 2 3 and 1 3. So remember the stabilizer of 1 2 or size of that and orbit of 1 2 size of that must equal 6 because this is the order of S3 and this is 3. So stabilizer of must be 2. What is it? Let's compute this. Stabilizer of this would be, remember there are some obvious elements in the stabilizer, G12, so I am doing more than what's in the problem. So really we have finished the problem. Problem was compute the conjugacy classes of S3, which I have done. But let's go ahead and do exploit whatever we have found in more detail. The stabilizer of 1 2 is elements of S3 such that G12 G inverse is 1 2, right? That means this is all group elements that commute with 1 2. So definitely E belongs to G12 and 1 2 belongs to G12, right? Because E certainly commutes with 1 2 and 1 2 commutes with 1 2, but order of G12 the stabilizer is 2 and it already contains two elements, namely E and 1 2. So the stabilizer of 1 2 must be E and 1 2. The counting formula tells us that we don't need to now check for other elements because the stabilizer must contain exactly 2 elements and it contains these 2 elements. So no need to make further checkings. This is the stabilizer of 1 2. Similarly, what is the stabilizer of 1 3? It also must be of size 2 and contain E and 1 3. Similarly, stabilizer of 2 3 must contain identity and 2 3 and must be of size 2. So this is the stabilizer. Finally, what is the stabilizer of 1 2 3? The size of the stabilizer must be 6 by 2 because the orbit of 1 2 3 is 3, right? Is 2. Orbit of 1 2 3 that we calculated has 2 elements, 1 2 3 and 1 3 2. So the stabilizer must have 3 elements. Stabilizer must have 3 elements and certainly E and 1 2 3 are contained in the stabilizer. And in fact, since stabilizer is a group, is a subgroup of S3 and 1 2 3 is in it, its inverse is also there. So inverse of that is 132. 132 is in the stabilizer. So G123 contains E, contains 123 and contains 132. But it is a group of size 3, so that must be it. This is of course also equal to the stabilizer of 132. Okay, so this extended problem here hopefully gave you a clear idea of the power of the counting formula and the class equation that we have computed, we have proved in a previous video. So again just to recap, action of a group on itself by conjugation is a very important example of a group action, and we have worked out in this problem fully all there is to work out in the case of the symmetry group on 3 letters. We first computed the conjugacy classes by looking at orbits of elements. There happen to be 3 orbits: orbit of E, which is 1 element, orbit of 1, 2 is 2 cycles, orbit of 1, 2, 3 is 3 cycles. So the class equation, which is simply the expression of the order of the set as a sum of sizes of orbits, in this case is 6 equals 1 plus 3 plus 2. There are 3 orbits of sizes 1, 3 and 2, so they add up to 6, and we noted that 1 divides 6, 3 divides 6, 2 divides 6, as we would expect, because orbit size divides the orbit of the order of the group. And then using the counting formula, we guessed, or rather we computed the stabilizers by first noting that stabilizers must have either orbit or size 2 or 3 depending on what element we are taking, and by picking obvious elements in the stabilizer we are able to compute the stabilizer of 1, 2, 1, 3, 2, 3, and also of the 3 cycle 1, 2, 3. Stabilizer of G123 happens to be the stabilizer of 132. Okay, so hopefully all these problems in this video gave you clarity on group actions, and the remaining content of the course would be using the class equation and conjugacy classes to prove some important results about finite groups called Sylow theorems, which we will do in the next video. Thank you.